At the end of the last video, we mentioned how you can use the number of impact craters on a surface to estimate the age. But how can we do better than that? Well, we can use radiometric dating. So here's the principle. Take a rock, and it will be composed of a ratio of what we're calling parent elements and the daughter elements. In radioactive decay, a parent element, this will be a heavier, higher number of protons and nuclei. That'll be the parent. The parent element, through natural processes going on at the atomic level, will just spit out and decay into lighter and lighter elements. So the parent's decaying into daughters. In this example here, you could start off with a rock sample that says it has 16 atoms of the parent. And each subsequent half-life, half of these parents have turned into daughters. So red represents the parent, blue's the daughters. After one half-life, half of the 16 have turned into daughters. So now the ratio is that there are 8 parents, 8 daughter elements. Go another half-life into the future, and you'll have 4 parents left, 12 daughters. Another half-life, 2 parents, 14 daughters. So by knowing the ratio of parent element to daughter elements and the half-life of that material, you can figure out the age. How old is that rock? Here's an important caveat that we need to make here. That age of a rock, it only goes as far back as to the last time that material was molten hot. When it's a molten liquid state, nuclei can freely shift around like a liquid. So when we say the age, we're talking about the last time this was in a molten state. Mathematically, you represent the radioactive decay to say that the change in the population, P is the population, the change in population divided by the change in time, that has to be proportional to the current population, right? So if there's a larger population, well, then the rate that population can change will be greater. And this can be turned into this formal equation that says the age of the rock is equal to this constant minus 3.3 times the half-life of the material. The T1/2 is the half-life, multiplied by the log of the percentage of final versus the initial population. Final population over initial population. So the important quantity here is this half-life thing. If we know the half-life material, we can measure what the final population is and get the age of the object. Here is one example of a decay chain that can happen. So the beginning process here will be lead-212, a higher, heavier isotope of lead, decaying to a lighter version, a lighter isotope, lead-208. And to spit out material to get rid of excess nuclei, it's going to do alpha or beta radiation. So in this decay chain, you'd have lead-212 spontaneously spit out a beta particle. A neutron, through this process, will spontaneously transform into a proton, and this will become bismuth-83. This is a unstable element, and so this bismuth will either spit out alpha, turning into a thallium atom, and then that thallium atom will spit out another beta particle, converting back down to the lighter lead-208. Or the bismuth could turn into polonium, spit out an alpha particle, and back down to lead. Notice that every time alpha particles leave, some nuclei are getting ejected out here, leaving the system. And that's how radioactive decay works. You're going from a heavier isotope to something lighter. In this case, you're going from one isotope to another isotope. Here are some other examples. You can go from carbon-14 to nitrogen. You can go from uranium to lead, potassium, and argon. There's all sorts of these examples. And look at these half-lives here. If you're going to talk about carbon dating, you're talking about this heavy isotope C14 down to nitrogen. And This half-life is about 6,000 years. Right? Now, if you want really good dating, say for ages of the planets or the moons, we're going to want to use the uranium to lead, uranium-238 to lead-206, which has a half-life about 4.47 billion years. You choose the correct dating tool for the age of the objects you want to study. When it comes to dating the Earth or the Moon, we definitely prefer moon rocks, and it's for one main reason. The Moon is not very geologically active. So when you go to grab a lunar rock, a lunar sample, you don't have to be too concerned about any volcanic or tectonic activity shifting that material around. As we look at the lunar samples, we'll find rocks that are anywhere between 1 billion to an upper limit that is 4 billion years old. Right? The number of lunar samples is just depending on the age. We notice there's a correlation between the impact craters, where we found the impact craters, and the corresponding lunar samples. So through our studies, we found that almost all the cratering on the Moon happened within the first billion years or so of the solar system. Coming back around to connecting this impact and the ages. Remember, when we say radiometric age of a rock, it was the last time it was molten. When there is a impact, you better believe that the material at that impact is going to become molten because of the sheer friction caused by this gigantic collision. So the radiometric dating of these impact craters will tell us how old the crater is. Taking this in action, let's look at a lunar rock. Let's say we have a lunar rock and we show that it has 15 times more lead-207 than uranium-235. Now, through studies here on Earth, we know that uranium-235 will decay into lead-207 with a half-life of 710 million years old. So with that, we can say, well, how old is this lunar rock? Remember that the age is given by that equation, minus 3.3, half-life log of the ratio of the final population versus initial. So, minus 3.3, our half-life is 710 times 10 to the 6 years. Log, right? We have, in this rock, we found there's 15 times more lead than uranium. So at this point in the lifespan, that rock, that lunar sample, is 1/16 uranium at its initial life, the initial stage. It used to be 100% uranium. So it was originally 100% uranium, that's why the 1. It's now just 1/16 of the rock, because the remaining 15 parts are all lead. That's where this 1/16 over 1 comes from. Plug in a calculator, you'll find this rock to be 2.8 times 10 to the 9th years old. Now, I like to try and focus on not using the equation too much. While useful, it's practical for getting these actual ages. Let's go to a more conceptual one. We'll just count half-lives and see what's the ratio of parents to daughters. Let's switch to our first question. So let's try not to use the equation. Let's do a different example. Let's say we have radioactive element A, and it decays in element B with a half-life of 20 seconds. Then after 40 seconds, what are you going to find? What are you going to see? Go ahead and pause the video and come back once you've come up with your answer. Now you're back. Let's work this out. After 2 half-lives, a quarter of element A is going to be sticking around. Not all of it's going to be gone. A quarter is going to be here. So let's go through this table, this chart. You work this out together. Initially, our sample is 100% of the parent element, A. And that would be at 0 half-lives. Now, if I go 1 half-life, or 20 seconds in the future, well then, half of A has decayed into B. Now go for 2 half-lives, or the 40 seconds that the question asked about. At 2 half-lives, half of this number has decayed away into B again. So we're now down to 25% of the parent element A, and this sample is now 75% of the daughter element B. Now, if we keep going down this chain, just for illustrative purposes, if we're at 3 half-lives, then A will now be 12.5% of the sample. B will be a growing majority, this 87.5. Keep going. Keep halving this ratio of the population. At 4 half-lives, A will be only 6.25%, whereas B will be 93.75%, and so on and so forth. That's what we mean by half-lives. Half the current amount of material will decay to the daughter every half-life.